Okay, welcome everyone to tonight's Reasons to Believe event. Next month, we're going to be hearing from Dr. Fuz Rana. He's going to talk about how the anthropic principle applies to biochemistry. So I thought it'd be good that we would review things that most of us have heard before about the anthropic principle as applied to other sciences. So tonight I'm going to do this presentation here. And this is basically the three things I'm going to answer here. What is the anthropic principle? And what are its implications? And what does what we learn here tell us about cause and effect? So over the last 100 years, various scientists have been noticing that there's different factors that are necessary for life to exist. Now, during the last 20 years, they've called it the characteristics you need for a habitable planet. And they've discovered that the universe has to be fine-tuned in order for life, for either bacterial life or even human life. And the fine-tuning for human life is much more stringent. There's many more factors required for human or advanced intelligent life than there is for bacteria. And this fine-tuning is actually called the anthropic principle. And anthropic comes from the word anthropos in Greek, which means man. So now we're going to look at, let's say, some of the history, some individuals that have been involved in discovering this idea and then telling others. So basically, it began around 1913 with Lawrence Henderson, who was actually studied psychology, but he was began to study other things too. And he proposed in 1913, he gave a series of lectures where he proposed that the environment is structured to have the necessary properties for life. And one of the things that he had discovered is that the body regulates the pH in the blood using carbonic and phosphoric acid as buffering agents. And it turns out that there's no other acids that are really suitable besides those two to have a good way of adjusting the pH. And if these two acids did not exist, then life would not be possible. And it was really a surprise at that time that would be the case, that there's nothing else besides what's currently being used by the body. And he also found out the various properties of water and carbon dioxide that make them essential for life. Then we have Fred Hoyle around 1953, who was investigating how various elements were produced in stars, because when the universe first began at the Big Bang, all you had was hydrogen, which later formed and then became helium. So those two substances were abundant, but none of the other elements were there. So Fred Hoyle and others were trying to figure out how do you get all the other elements that exist. And they concluded that they must have somehow happened when stars went supernova, and you produce other elements as the heat of the supernova caused atoms to combine together. So Fred Hoyle theorized this formula here that's in this diagram, where you combine two heliums to produce beryllium, and you give off some gamma rays. Then this beryllium combines with another helium, gives off another gamma ray, and produces carbon. And he found that this only happens if you have a certain energy level for the carbon and for the beryllium. And there's a similar sequence that is for the production of oxygen. And in order to, because if you look at the amount of carbon and oxygen in the universe, you get that there's pretty high amounts of both of them. And the only way you could produce that in a supernova would be to have the proper energy levels for carbon or for beryllium and oxygen. And so he thought seemed like kind of a coincidence, he thought. But he didn't really see this as necessary for man or for life. So he never really considered it as being fine-tuning for life.
Yeah. Why?
So next we have Robert Dick in 1961, and he realized that life is only possible in a certain period of time in Earth's history. We know that life requires certain elements, like carbon and oxygen, like we talked about. But in order to have enough of them, you have to have enough stars that have gotten to a certain point in their life where they went supernova, because that's the only place you can produce those elements. So first you have to have the stars form, then they have to grow basically old to the point where they go supernova. And then when they explode, then they produce these elements. So you cannot really have any life in the universe until that happens. And I think the minimum point in time where that could happen would be when the universe is 7 billion years of age. If you wait too long, then there's not enough elements formed. And there's another issue, like you have to, I forget now, let me see. You also need to have a certain amount of metal elements that are heavier so that you could have planets form, because you need to have a solid surface for the life to exist. So you need to have enough silicone for, to have solid matter, and you need to have uranium and thorium for a core in the planet. So that all takes time. So until you get to that point, you can't have life. Then in 1973, Brandon Carter wrote an article where he concluded humanity lives at the just right time and location in a universe with the just right physical constants. And he was the first one to use the term anthropic principle. Then in 1986, John Barrow and Frank Tipler wrote a book called Anthropic Cosmological Principle, where they realized that the various constants of physics have to assume precise values so that life that's based on carbon can exist. And since then, others have proposed that life could maybe be based on other elements besides carbon, but none of them work. Like silicone is similar to carbon. It has a valence of 4, but because of the mass of the silicone, you can't have more than, you couldn't use silicone to make proteins that are more than about 100 chains of amino acids, because it'd be too heavy and it wouldn't have enough attraction to hold them together. So carbon is basically the only type of life that's possible, carbon-based life. So now let's go through some of the factors that are involved in the fine-tuning. So we're going to start with having the correct mass of the universe. This chart gives you more or less what the whole universe is composed of. 72% is actually dark energy. 23% is dark matter. And the rest is regular matter, which is hydrogen, heavy elements in the planets, neutrinos, and hydrogen and helium in stars. And you need to have the right amount of material. Can't have too much mass, because otherwise then it would not expand properly and it would collapse, possibly collapse, because the gravity is too strong. If you don't have enough matter, then you don't have enough stars being produced, so you don't have enough supernovas and so on. And everything leads to more other issues. Then you need to have the right expansion rate and the right cosmological constant to have the expansion go at the right rate, so that then you could have stars forming. And let me just see here, I'll give you more details about this here. Yeah, if the expansion rate was too big, too fast, then you wouldn't be able to form galaxies because the matter would be spread out too much. If it's smaller, if it's not expanding fast enough, then the universe would collapse, and then you wouldn't have any stars forming either. Then you need to have the strengths of the different forces in physics be balanced correctly. You have the nuclear force that binds the protons and neutrons together in the nucleus. You have electromagnetic force that binds protons to electrons. You have a weak force in the nucleus that affects the rate of radioactive decay. And then you have gravity that affects how planets can orbit around stars. Then you need to have the relative mass of electrons and protons to be balanced correctly. Or if you compare an electron to a proton, the relative mass is about 1836. The neutron is slightly more because the neutron is actually a proton combined with an electron into a single particle, so that the proton charge cancels out the electron charge, and the neutron has a neutral charge, and that makes it slightly heavier than a proton. And you need to have an equal number of protons and electrons. The theory is that there was protons and antiprotons and electrons and positrons, which collided with each other and then canceled each other out. So that what was left had to be an equal number of both. Otherwise, if you had different numbers, you would have a net charge of the whole universe, which we don't see that at the moment. And you need the right kind of galaxy. The only galaxy that really can support life is a spiral galaxy. There's about 5% of the galaxies in the universe are spiral. Here's what we think the Milky Way galaxy looks like. No one can see it because we're inside of it, but they figure this is what it would look like if you were far away from it. The Andromeda galaxy is the nearest spiral galaxy. So, and the other 95% of the galaxies in the universe, you can't have life because, let me look this up here. If you have an elliptical star, then you would not have enough stars being produced because it would stop at a certain point. If you had, there's two other types of galaxies besides elliptical. Those are, besides spiral. One is called elliptical and one is called irregular. And if you have an irregular galaxy, then the radiation exposure would be too severe, and it wouldn't be as many heavy elements produced. And then you also have to have a right number of supernova explosions to produce all the elements that you need. Here's a diagram that shows two types of supernovas depending on the star that you start with. A star like the sun, at a certain point in its age, about 7 or 8 billion years old, it expands to become a red giant. And all the outer layers dissipate. Then the center that's left contracts to be a white dwarf. If you have another star orbiting that star, which you call a binary star, then the material from one gets sucked into the white dwarf, and it keeps on adding material to the white dwarf until there's a certain point where it becomes 1.4 times the mass of the sun. And at that point, it'll go into supernova and explode. And this whole process takes about 10 billion years. If you start out with a really heavier star, like here, for example, if you have one that's 8 solar masses, it also at a certain point expands, becomes a red giant. And then the center collapses to be a blue, what they call a blue star, which eventually then explodes as a supernova. And this process takes only 10 million years. So depending on how many of these bigger stars you have compared to the smaller ones will determine when you'll start having extra elements. And you need to have these supernovas to be the right distance from a planet so that you can produce the elements that the planet needs to form. And often enough, or not too often, at the right time in the age of the universe. Then you need to have fluorine for life, actually. Fluorine is an element that's produced in only one place in the whole universe. When you have a white dwarf with another star orbiting it, and the material coming off of this star gets pulled into the white dwarf, and the fluorine is produced on the outer edge here as this gas spins around the white dwarf, it can form fluorine, and that's the only place. So you need to have enough the right number of white dwarf stars in order to produce fluorine. Then you need to have your planet has to be the right distance from the center of the galaxy. If it's too far away, you don't have enough elements, because it gets rarer and rarer. If you're too close, you have lots of extra radiation that would kill any life that formed, because the center of the galaxy has a supermassive black hole that's producing lots of radiation. For example, in our Milky Way, the black hole in the center weighs about 4 million times the mass of the sun. And you need a just right solar system that has only one star in the center. If you have a binary system where you have two stars orbiting another, it affects the orbits of all the planets going around it, so you don't get stable orbits. You have to have the right mass of the star. If the mass is heavier, like you saw in this other diagram back here, when you have a bigger star, it doesn't live as long. It only lives 10 million years. So if you have a star that's too big, you won't have enough time for the planet to form and to have life on the planet. And you need to have the right color so that the color of the light that's hitting the planet can produce photosynthesis. Here's an example here of three colors of stars. A cooler star, which is, you can't really see, it doesn't produce much light. A star like the sun, which is mainly yellow. If it's hotter, the light from the sun is actually bluer. And so you need a yellowish color in order to have enough light that produces photosynthesis. And something else I wanted to mention here. So any color other than the yellow would not have enough photosynthesis. Then you need to have planets about the size of Jupiter and Saturn, also part of the system, because these planets, because they're so heavy, they attract any asteroids or meteorites, and they would protect the planet that's on the inner, closer to the star, so that you wouldn't have a lot of asteroids impacting the planet. You need to have a moon, and the moon has to be big enough to produce, in order for it to protect the planet. Like the moon, for example, keeps the Earth at the right angle here of about 23.5 degrees, keeps that stable. Otherwise, this angle would switch, alternate back and forth. And it also produces tides, which helps the organisms in the ocean. Like our moon being, so big compared to the Earth is an unusual phenomenon. In our solar system, there's no other planet that's got that same ratio, huge ratio of the mass of the moon compared to the mass of the Earth. And you need to have the correct mass of the planet so that you have enough gravity. If the mass is too low, it's not strong enough to hold all the atmosphere, so the atmosphere is very thin. If it's too heavy, let me see what happens if it's too heavy here. If the gravity is actually too strong, you end up getting too much ammonia and methane in the atmosphere. And you have to be the right distance from the star. Here, this green part around the star is the place where you could put a planet that would enable you to have the right temperature so you could have liquid water on the planet. And this is called a habitable zone, which many scientists are thinking that they found planets that are in this habitable zone. But that's not the only requirement. Like, so far, we've already looked at about 10 different requirements. And you need to have that axial tilt that I showed you before in this diagram here. This helps to, if you didn't have an axial tilt, it would actually affect the climate to an extent that would make life difficult or almost impossible for, advanced life. It'd be probably okay for bacteria, but for us, we would need to have a more stable climate. You need to have the orbit around the sun to be, very close to a circle. You can see from this diagram that the orbit of Mars is not a circle; it's sort of elliptical. When Mars is at this point here, it's closer to the sun than at this other point here at the top left. So when Mars is up here, it's colder. When Mars is over here, it's hotter. If this happened on some other planet that had life, then the climate would change drastically. Then you need to have the right rotation period. Right now, we have the planet Earth is 24-hour a day. When the Earth was first formed, it was about a 10-hour day. And it's slowly gotten longer, partly because of the moon, the gravity of the moon slowing down the rotation of the Earth. If you have it to, let's see what we say here. If the day was longer, you'd have too much of a difference in temperature between the day and the night. If it was shorter, you would affect the wind velocity of the climate. The wind speeds would be so much greater when your length of the day is shorter. You need a planet with a magnetic field. The sun emits radiation, and when it hits a magnetic field, it actually is deflected away from the Earth so that it doesn't hit us. If we didn't have a magnetic field, the radiation would be too high and life couldn't exist. Now, you also need to have a crust on the Earth that has to be the right thickness. If it's too thick, you would have too much oxygen be transferred from the atmosphere to the crust. If it's too thin, then you wouldn't have enough volcanoes and earthquakes. And you actually need volcanoes and earthquakes because erosion constantly takes soil from the land and dumps it into the ocean. And the only place you get extra soil is from an earthquake or a volcano spewing extra material onto the continent. And you need to have the right percentage of land versus ocean. And then, of course, you need in the center and the core of the Earth, you have uranium and thorium that's producing the heat in the center. If you don't have that heat, you can't have you can't have any volcanoes because the lava is not warm enough to escape out and produce the volcanoes. Oh yeah, Peony just mentioned here, I just noticed it now in the chat that this is called the Goldilocks zone, to have all these characteristics for life, to have, the story of Goldilocks that went to the bear's house and found porridge. One was too hot, one was too cold, and one was just right. So our universe is just right. Have the right amount of oxygen, nitrogen, and water vapor and ozone in the atmosphere. And this sort of tells you approximate percentages of each. So if the ratio of oxygen to nitrogen has to be right. If it's larger, then your metabolism would be too quickly. If it's smaller, then it would proceed too slowly. You need the right amount of carbon dioxide. If you have more carbon dioxide, you have a greenhouse effect, which is would affect global. Just like now, people are concerned about global warming. It's the same way. If you have too much carbon dioxide, it'll be too hot. You need to have the right amount of water vapor. And the same way, water vapor produces the greenhouse effect as well. And if it's too little water vapor, you don't have enough rainfall. Then you have ozone that's in the upper atmosphere. It protects us from ultraviolet light. So if you have too much ozone, you have the temperature would be too low on the surface. And if you had too little, you would have too much ultraviolet radiation. You need the right amount of oxygen. So if you have too much oxygen, then you have plants and hydrocarbons burning up. If you have too little oxygen, you don't have enough for animals to breathe. So as of 2008, Reasons to Believe has a chart on their website that shows all the different characteristics. And so as of 2008, they've discovered about 816 that correspond to factors that affect human life. And yeah, as far as I can tell, they haven't updated it since then. But I'm not sure why, except that, you know, when you have this many factors, what more evidence do you need? It's the chance of all these things happen naturally would be 10 to this exponent, which, you know, over 1,000, which is a number you can't even imagine how big that or how small that is. So why is there fine tuning? John Barrow and Frank Tipler, in their book, they suggested 3 possible things that could cause this fine tuning. One is they thought that it could be the product of observer-created reality. I'm going to explain that in the next slide in more detail. Then they thought that the other possibility is a multiverse, where you have a huge number of possible universes, and they all have different constants, and we exist in the one that's just right. Or the universe is the work of an intelligent agent. So observer-created reality is that they think that somehow we, being the observers, have created the universe to be something that would enable us to exist. And they base it on experiments in quantum physics. And let me explain how this works here. If you have a wave being shot at an object with 2 little holes in it, as the wave of light goes through it, the wave from this hole interacts with the wave from the other hole, and it produces a pattern where they have patterns of bright and dark light. Now, when you shoot electrons, electron is considered to be a particle, but turns out it's also a wave, because the pattern that it produces when it hits this detector here is the same as if it was a wave. You have different bars at different locations. But if you actually shine a light or a sensor here that looks at these electrons, and you only fire one electron at a time, so that you can tell, you know, I fired the electron, oh, this one went through this hole. Fire another one, oh, this one went through that hole. The pattern that you see on the end, when you put a detector here, is only two single bars. You don't see all these other bars. So somehow, by you observing what the electron's doing, you've affected the path of the electron so that it only forms 2 bars here. So the way they interpret this is that by you observing an effect, you change what it's doing. So then they extrapolate this to to the whole universe, and they say that by us observing the universe, we're somehow affecting reality and changing it to give it the characteristics that we need for life. But to me, that's not right, because you're assuming that what you see on a quantum level can be extrapolated to happen on the whole level of the whole universe. And quantum effects, to me, cannot be extrapolated that way. So this, I don't think, is a valid way of looking for a solution. The other option is a multiverse. And in order for the multiverse to work, there's a book by Jeff Swearing. I don't know if you've seen this book, Who's Afraid of the Multiverse? He talked about this idea of the multiverse. Yeah, someone here in the chat said what I talked about before about observer created reality is a crazy idea. So anyways, the multiverse itself, in order for it to work, you'd have to have some way of generating all these infinite types of universes, and they have to be able to be different enough so that one of them would be fine-tuned for life. But how do you create such a possible mechanism? How do you make an infinite number of universes where all the known factors of that universe is different from the others, and to have one of them be fine-tuned? And no one knows of such a mechanism. And there's really no testable predictions for it, because the multiverse could not be detected. Like whatever is in one universe could never detect anything that's happening in another universe. Hugh Ross did mention in one place that there is some type of, there are some models of multiverses where you can maybe detect something in our universe. Hilmar sent that to me, but he's not here to give me any more explanations of what he meant. But even then, there's very few testable predictions, so it's not really a scientific theory. And even multiverses that are created by inflation expand, so that, in a sense, and this Jeff Zweering talks about it more in his book, that even if you have multiverses, they all have a beginning. So again, it points to somebody that started the whole process. So then we come up with the most obvious explanation, which is that an intelligent agent, by that I mean God. And the Big Bang Theory, we know that indicates that the universe has a beginning. And if there's a beginning, it requires something to start it, a beginner. So those factors that I talked about for life is extremely low probability of that happening. 1 in 10 to this huge exponent here of over 1,000. Now I want you to imagine an analogy that Hugh Ross and others have thought of. Let's say you are somehow accused of a crime and you're sentenced to go in front of a firing squad. As you're waiting there to be killed, everybody shoots, but you're still here. You're not dead. So what's the explanation? Did everybody just miss by accident, or did they plan and just purposely aim away from you? What's more reasonable? And it's more reasonable that they plan not to kill you. That couldn't have everybody missing by accident, because the probability is so low. So the simplest explanation is that the whole universe was fine-tuned, and because it was designed that way. I think Ian asked a question here. I think he's referring back to this experiment here, where they fired electrons one at a time. An electron, because it's a particle, you can set up a device where you can fire one at a time at the slit. If you, in this case here, they would do the same thing, fire an electron, see a pattern here, fire another electron, see where it lands. Well, actually, they wouldn't know where it lands. They just fire one at a time with a bit of time in between each and just look at the final pattern. But they wouldn't know which electron went through which hole. Here, because you have a sensor, you're still firing one at a time, but you can tell which hole it goes through. I don't know, Ian, if that answers your question. Because you can have a device like an electron beam that would produce only one electron at a time, and then you could do this type of an experiment. So what's the implications of all this? As I said, the most reasonable explanation is that God designed the universe for humanity. And the degree of fine-tuning is so high that it means that God who designed it must be more intelligent, creative, and powerful than us. And as Hugh Ross says, they must have a lot more money than us, than the US government, to create such a fine-tuned universe. And there is evidence that God intervened several times after the original creation, after the Big Bang. It's not that God just started the Big Bang and then went on a holiday. And one of the things, for example, that would require an intervention by God is simply the production of the solar system. Our Earth has a huge amount of uranium and thorium in the core to produce, hot enough core to have the right amount of volcanoes and earthquakes. It turns out that the only place you can produce that much uranium and thorium is in the center of the galaxy, where you have a much higher density of stars. But you couldn't leave the system there, because then you wouldn't have any life there, would be destroyed by the radiation. So it seems that the solar system was created in the center, but then moved out away from the center in one of the spiral arms. So I believe that God intervened to actually move the solar system from the center to one of the spiral arms. And this whole process of creating and all this fine-tuning implies that God must love and care for his creation. So if you have intelligence, attention, and love, it implies that God is a personal being. He's not a distant God. This is referred to as deism, where you say that, okay, maybe a God created it, but he's not involved now, but we know that he's still involved. And so this deism is not a valid idea of who God is. And that means, of course, that life has meaning. If there's a God who created us, he must have a purpose for creating us. So what does all this tell us about cause and effect? We know that because of life requires a whole series of fine-tuned parameters, it means that I think this applies to anything in life, that when you have a complex effect, it requires a multitude of fine-tuned causes. Here's a chart that I got from a website that I don't think whoever designed this is Christian, but they made this chart that shows, all the different things you need for a habitable planet. And this applies, I think, to other areas as well. And I want to look at 3 different examples of complex problems in our world that require a multitude of things and complex problems that require a multitude of things to fix them. One is in software development. Some of you that listening are probably involved in writing software. I don't know if you've heard of Fred Brooks. In 1986, he wrote this article called No Silver Bullet about finding a solution to the issues of software. All of us have probably been aware of software that was released late or buggy. So in this article, they include a picture here of a lady you can't see in the background, but she's running away from a werewolf, because the legend is that a werewolf can only be killed by a silver bullet. So people that write software are looking for one particular solution which will enable them to write great software with no bugs. And Fred Brooks wrote this article saying there's no such thing. You can't. You need to have a whole bunch of things that in order to have the right to have good software. Dementia and Alzheimer's. In 2017, a researcher named Dale Bredesen wrote a book about Alzheimer's and how to actually reverse it. And he found out that there's 36 different factors that affect your brain health. And he made an analogy of saying, let's say you have in your house, you have 36 holes in your roof. And when it rains, you get water coming in. How do you stop the rain? Well, you got to plug up all those 36 holes. Plugging up one or two won't help. And after writing this, I wrote a review on Amazon. Let me just read to you some of what I wrote here. And I wrote down that the current view of Alzheimer's is that it's a disease caused by the accumulation of plaque in the brain. And the way you treat it is to stop the plaques from forming, or you remove the plaque once they formed. And most drugs that are developed with this basis have succeeded in stopping or removing the plaques, but the person didn't get any better, and sometimes even got worse. So Dale Bredesen says that what Alzheimer's really is when the brain responds to various effects by downsizing. And apparently there's 3 different types of Alzheimer's, and each is a response to different triggers. The first one is caused by inflammation, caused by too much sugar, infections, or other causes. Second one is not enough nutrients in the brain. And the third one would be toxic exposure, such as metals or biotoxin. So the way he has cured many people, the second book here is actual personal stories of patients that have recovered from Alzheimer's. And you need to actually look at all these 36 factors and fix each one. And when you fix enough of them, then the patient gets better. You all heard the saying, an apple a day keeps the doctor away. Is that really true? I don't think it is, because good health is not just one thing. That goes back to what Fred Brooks said about no silver bullet. You can't just do one thing and be healthy. You need to have good nutrition, sunshine, vitamin D, enough sleep, enough exercise, low stress, avoid toxins, and so on. There's probably more. So to me, majority of things require a multitude of things to fix them, any problem that you encounter. But there are some simple things, actually. Hugh Ross calls physics and chemistry simple sciences, and everything else complex. So like, in physics, that when you apply a force to something and it moves. Newton's laws of motion. The most basic one is that the force you apply an object of a certain mass produces a certain acceleration. In chemistry, elements react to form other compounds. In your furnace, you burn methane with oxygen, and you produce water and carbon dioxide. These are the simple things. Most other cases of things are more complex, and have more factors involved. So the things that have a simple solution, for example, if you can't start your car, you probably need a new battery. If you try to plug something into an outlet and it doesn't work, you probably need to reset the breaker. But even that is, a complex system could have a simple solution if there's only one part in the complex system that's malfunctioning. So you fix that one part and it starts working again. When you have a bacterial infection, you use antibiotics and you kill off the bacteria. But then, of course, you get a side effect of creating bacteria that are resistant to antibiotics. We know that the only solution to sin is Jesus. The blood of Jesus Christ, his son, cleanses us from all sin. And there are cases where one cause will have multiple effects. I don't know if any of you have heard of the butterfly effect. Back in the 60s, Edward Lorenz was trying to write software to predict the weather. And his system came up with this effect where if you change something initially at the start, something that's so small, it's as if a butterfly was flying in a certain place, it would then cause an effect which would spread out and cause a change in climate some other place far away. But it turns out that the model that he used is not accurate, that the models they use now show that a butterfly has such a small effect that it would all fade away. It would all decay. And what really affects the weather is things like wind speed, air pressure, and the number of clouds. And it's sort of kind of difficult to measure those precisely. So in the computer models they have now, if you change the wind speed slightly or the air pressure slightly, it does cause an effect further down the road. And because we can't measure it, we can't predict the weather ahead more than 3 days or a week ahead of time accurately. We know that there are mutations in your DNA can cause much suffering and pain, cystic fibrosis, sickle cell anemia, and other diseases. And we know that one bad decision sometimes can have multiple devastating consequences. So in summary, what I've talked about is that the universe is fine-tuned for life. And that God is the explanation for this is the best explanation is that the fine-tuning was designed by God, a God who lives outside of the universe. And we know that life, which is a complex thing, requires a multitude of complex causes. So here's different things you can look at to get more information about this. If you go to this website, this page here on the Reasons to Believe website, they have a lot more information about fine-tuning. If you read any of these books, you'll find out more. This last one here, Fit for a Purpose by Fazal Rana, just went into print a few weeks ago. And next month, we're going to have Fuz come and talk about this. And you can buy most of these either at the Reasons to Believe website, or go to Christian bookstores, some have them as well, or Amazon. So if after tonight you think of more questions about this, you can contact us at either of these emails here. So that's all it for my talk. I'm going to open it up now for questions. So I'm going to stop sharing the screen. And if anybody has any questions, unmute yourself and go ahead and speak.
I'd just like to mention, Bruno, once again, the book that I spoke of earlier on is called The Return of the God Hypothesis by Stephen Meyer. He also wrote a book called Darwin's Doubt. But that book, The Return of the God Hypothesis, covers a very large number of the things that you have been referring to tonight. And it's very well written. I'd recommend it to anybody to read.
Okay.
I've got a few questions here I wrote down. I'll just ask one.
Okay.
What's the relationship of the moon to the Earth? How does it go about keeping the Earth tilted at 23.5 degrees? What exactly is the moon doing to make that happen?
As far as I know, it's just a gravitational interaction. It keeps the Earth stable. I don't know the exact mechanism of it. If somebody else knows, that maybe they can explain it.
Actually, we have the short answer is, yeah, Bruno's right. It's gravitational
relationship between the Earth-Moon system. But there's a really excellent DVD on this that perhaps we could show at a future RTB event, Bruno, all about our moon and why it's so important for life on planet Earth. Our moon is very unusual. Most moons are not 1/4 the mass of the planets that they're in orbit around. So our moon is unusually large.
Is that the video that we saw maybe about 3 or 4 years ago? At one of our meetings?
I'm just looking it up here. I don't think so, Bruno.
Oh,
The one I'm thinking of, just give me a second, is called "If We Had No Moon," and it wasn't necessarily a Christian production, but I'm just going to show you a picture of it. That's what it looks like.
it sounds familiar, but I don't know if that's the one we saw. We saw something
Anyway,
similar to that.
anyway, maybe we'll watch it
Yeah,
again
that's-
sometime.
Yeah, sure. Sounds like a good idea.
I wonder if it's could be because there's more continental mass in the northern hemisphere. Would that have something to do with it? That gravitational pull would affect the continents more than the oceans?
Yeah, that's a good question, Andrew. Because you're right. If there's a differential in the mass of the Earth, you would expect it to affect it in that way. All I know for sure is from what I've read in the various books and stuff is that the 23.5 approximately degree tilt of the Earth, which gives us our seasons and is vital for life on planet Earth, is directly related to the moon. But that's not the only thing. Our entire tidal system, as you know, is completely dependent on the moon,
Of course.
the size and amount of our tides. So again, you know, the distribution of mass I'm not sure if that would really make a big difference, because now you have to account for, you know, where the oceans are as well as where the rocks are, et cetera, et cetera.
Bruno, you were talking about, you know, uranium and thorium and all the heavy elements in the planets. Why
Yeah.
wouldn't the sun have attracted all of the heavy elements? Because it had massive gravity at the beginning, but it was primarily hydrogen and helium with obviously some other elements. But we got all the heavy elements, you know. Is there any reason for that? Do you know?
Well, you have I talked about the supernovas that produce all the heavy elements. So those would have all been orbiting in a big cloud, you know, and all the hydrogen and helium would have condensed in the center to form the star. You know, the other material would be spinning around it. And like I said, the whole solar system, in order to have that much uranium and thorium, had to have been very close to the center of the galaxy in order to get, because that's the only place where you can have enough uranium and thorium. Because there's so many stars, you would have had so many go to supernova that would have produced the uranium and thorium. And that's the only place to get enough of it. And then that whole system, once the star system formed, you would have to then move that whole system out into one of the spiral arms. But,
Oh, okay. Okay.
so the reason why you have all the thorium is because, or the only way you can get the thorium and the uranium is to have the star system be formed close to the center of the galaxy.
Okay.
Bruno, can you remind me of this question? So in the center of our spiral galaxy, the Milky Way, there's actually a black hole, right? But what keeps the whole galaxy from being sucked into the black hole? Is it a dark matter? Is it the mass? What exactly balances the black hole? Can you explain that?
Let me go and get my thing here and share my screen again here. There's a diagram I want to show you here. Where is it here? Share my screen here. Let's go back here to back near the beginning here. Right here. So this is, our galaxy is actually spinning. We're moving at actually 240 kilometers per second, orbiting these the black hole in the center, because we're orbiting the same way how the moon doesn't fall onto the surface of the Earth, because it's orbiting around us. You know, we don't fall into the sun because we are orbiting around the sun. So the same way all these stars are orbiting around the center, and that's why they don't fall into the center.
I see. So it's like a centrifugal or a centrifugal force, I guess, in a way.
Yeah, you know, that's pretty fast. 240 kilometers a second. That's pretty fast.
Yeah, I just saw there's some really amazing documentaries through Nova about the black hole findings, with the dark matter and the dark energy, and then they discovered that the whole idea of the swirling galaxy is this black hole in the middle of every one of these galaxies. There's billions of these galaxies, right, that are like this.
Yeah.
But in
Yeah.
the universe, it's pretty tremendous, amazing. Yeah, thank you very much.
And like I said, we're located in one of these spiral arms, and we're actually not on the spiral. We're actually in between two spiral arms, so that we don't have a lot of stars around us. And that actually helps us because we have so many stars far away from us. That actually enables us to see outside. If we were had too many stars around us, it would be too bright at night, and we wouldn't be able to take pictures of all the different galaxies that are far, away from us. And we would be in a bad spot to actually study astronomy. So we're actually in the right spot to actually be able to observe all these things and to discover what God has done. If we were somewhere else, we wouldn't be able to discover it. And if we wait a couple of million years, we'll see less and less of the universe. And if God had created us, a few billion years earlier, we still would not be able to see enough of the universe to actually discover all these things about him.
So you're saying that this centrifugal force that is balanced by gravity that keeps things a constant distance away.
Yeah.
Because I thought there was the dark energy. And I have a question about dark energy. Does it play a part in that, maintaining that distance as well?
I don't know. Don, do you know?
No, dark energy is on a much larger scale, Andrew. It's not on a intragalactic level. It's on an intergalactic level. So dark energy essentially is one of the primary drivers behind the expansion of the universe, which is that stretching of the fabric of the universe that takes the matter that's on the fabric, as it were, fabric in quotation marks, that drags it further and further out and stretches out the universe. So it's operating essentially on a universal scale, not on a galactic or
you were saying that
solar scale.
You were saying that it's 73% of the universe's mass. So
actually, one of the proofs for dark matter is that they've looked at the spin rate of galaxies, and it's not right. There was a problem, and they had to speculate about dark matter in order to get that spin rate to match, because if it was just the observable matter, it wasn't spinning at the right rate. It didn't have enough mass for that spin rate to be stable. So
Paul's absolutely right. Yeah, we can only see 4% of the visible universe. It's only 4%. So there's a whole lot of other stuff that we can't see.
Mm-hmm.
I actually had a question, Bruno, or kind of a question and comment. So for many years, I kind of assumed that the anthropic principle was kind of like a trump card if you were trying to present a case for a designer or for a creator. And what happened fairly early on in my sort of apologetics journey was I ran into people who actually were making the case for the anthropic principle, but were absolute avowed atheists. And the one that comes to mind is, I've got his book here in front of me, very famous guy, Michael Denton, who wrote Evolution, A Theory in Crisis, but he followed it up with another book called Nature's Destiny. And the subtitle of the book is How the Laws of Biology Reveal Purpose in the Universe. So if you were to pick this up, you know, you'd be forgiven for thinking, well, this guy must be a Christian, but he's not. So I found that quite interesting. And of course, there's lots of, you know, other scientists out there who talk about the anthropic principle, but don't make that jump to faith or belief in an actual personal God. Would you like to comment on why that might be? What are your thoughts on that?
Well, my opinion is that you can present the evidence to someone, but if they don't like the conclusion, they'll sort of block it out of their mind somehow and rationalize why that's not a possible solution. Even when John Barrow and Frank Tipler wrote this book, they had three possible reasons, like three possible causes for the fine tuning. Either something about what they call the observer created reality, which doesn't make sense, the multiverse, or God. So if they don't like God, they can choose one of the other two as their preferred answer to where this came from. You know, there's a lot of smart people in the world, but if you don't want to believe something, you'll rationalize it away, is my opinion.
They could say there was a natural explanation for it. We just don't know what it is yet. But that's the leap, the same as the jumping to the God explanation is a leap as well.
Yeah. Hugh Ross tells a story of talking to somebody and presenting all the evidence for God, but the person wouldn't believe because it mean if God was real, he'd have to get out of this relationship that he's involved in with another woman that is not not kosher, and he didn't want to do that, so you wouldn't believe in God because of that. Anyone else have any questions?
I was going to ask you if carbon dioxide is it's necessary for life, but is it necessary directly, or is it just part of the atmosphere so you don't have a disproportionate amount of oxygen? Oxygen is sort of not as what do you call it? Too much oxygen would cause life to be shorter. But do humans actually absorb or use carbon dioxide in any way?
No, but plants do.
Plants do, yeah.
If
So
people are concerned about carbon dioxide in the air causing climate change, but if you reduce the carbon dioxide too much, it'll actually affect the growth of plants. You won't get enough crops. You won't have enough food. Have the right balance.
Actually, there's another aspect too, Andrew, and that is our brains tell us to breathe not because of a lack of oxygen, but because of a increase in level of CO2.
Right.
So
Yeah.
CO2 actually regulates a lot of our metabolism. So yes, the short answer is it's absolutely vital.
Okay.
To life of humans, but the big one, of course, is plants who fix nitrogen and use carbon to make sugars, which we consume, and so forth and so on. Something
I've picked up in my reading, I'm not sure I can conclude this, but I suspect it that the atmosphere needs biological life, and of course, biological life needs the atmosphere. So this is sort of like a chicken and egg thing. One didn't come before the other. They sort of moved along at the same time in the development of the earth, and it's preparing for complex life.
Absolutely.
That is true.
Well, yeah, you need to have the right conditions before you can even have the life to start with. So when the first bacteria came about, you had to have, liquid water. And there was a certain point in history where the planet was being hit by asteroids so much that the surface had become basically molten lava. Once that stopped, then the crust could cool, and then you could get liquid water on the surface. And at that point, then you could have bacteria. Not before.
Right. Yeah. So they move along together in this history of the development of Earth.
Yeah.
Yeah, you can't have an atmosphere. Okay, now we're ready for biological life. They kind of move forward at the same time.
Yeah.
One of the other things I thought I'd mention,
Can I
Bruno, is
oh, okay,
just,
sorry. Yeah.
oh, sorry. Yeah, I'll just finish. It's, you mentioned a number of parameters that are necessary for life, but, and that those values of those parameters need to be quite precise. But I think you might want to just add a little bit, Bruno, for us to help us understand that it's not just that the value is X or Y, but that the value can't vary by hardly anything. And then life would not be possible. And just one example was, I remember listening to a lecture by, I forget his name now, but he may still be actually the head of the physics department at the University of Waterloo. And he gave a talk on the Hubble constant, the expansion coefficient for the universe. And he said, when I say that this is precise, I mean, it's precise to the 14th decimal. If you vary the 14th decimal by 1 up or 1 down, there's no universe. I thought, okay, that's precise. So you might want to add, maybe just comment on that, Bruno, just to give us a greater sense of wonder as to how amazing these numbers are.
Yeah, like I think it's the expansion rate, or one of these two here, either the cosmological constant or not, has to be precise to the 100th decimal point or the 120th.
That's the cosmological constant, yeah.
Yeah. So this is something you can hardly even imagine. In the whole universe, you only have 10 to the exponent 80 particles. So imagine if you just removed one, the whole system wouldn't work. Hugh Ross gives an example. At the beginning of the universe, if you remove the dime from the mass of the universe, it would expand at the wrong rate, and it wouldn't work out. You wouldn't be able to have life. Just a dime in the whole entire universe would make it expand at the wrong rate.
At the beginning, yeah.
At the beginning. If you change it later on, it wouldn't make much of a difference. But at the very beginning, where it expands at this inflation period here. So that's something you can't even imagine has to be that accurate.
Sorry, Don, I was just wanted to point out that documentary, I put in the notes in the chat it's actually on Netflix. It's called, it talks about the black holes. It's called The Edge of What We Know. There's a couple of documentaries there, but maybe elementary for some of the astronomers and mathematicians. But I found it very interesting about the black holes. To balance the spiral on these things, they're saying that the new findings have been with this, the dark energy, or I guess the dark energy, it creates the right mathematical coefficients to make the actual spin rates make sense. And recently they've used old methods of analog, like taking pictures and piecing it all together. They go over the whole complex process. But now with supercomputers and new telemetry and new algorithms, they sped it all up. They can make models of this stuff because we have the computational processes to do it. So my question then becomes around the new James Webb Telescope, using infrared and different types of frequencies. I'm sure many of us have seen the documentaries. What do we suspect, Bruno and Don and others that could come in on this? What do we expect to see about these coefficients and the different fine tuning and that's going to come out of this? What's our expectations?
I'm sure that they're going to discover a lot with the James Webb Telescope. Exactly what, I'm not sure. Don, do you have any idea what they expect to find?
No, but I would probably defer to Paul or Renko on that one. I mean, this is the most amazing telescope ever built by far. It makes the Hubble look like nothing, and the Hubble was incredible. So, yeah, Paul.
I think one of the main things they're looking for is even better proof of exoplanets, because it's going to be able to resolve so much higher than the Hubble and look so much farther. So I think they are really counting on it being able to look even at the atmospheres of exoplanets, perhaps, which is mind-boggling to me, but yeah.
I think the thing that I'm excited about is the so-called look back time. We can currently see back to about 380,000 years after the creation event. And from what I've read, the James Webb is going to be able to push that back even farther, and they'll have a lot more data. So they'll be able to see, galaxies in the very, very earliest stages of their formation in much greater detail than what the Hubble has been able to see.
Mhm.
So if you can imagine, I don't know if you've seen that picture from the Hubble, it's probably the most famous one, which is the so-called deep field shot, where they trained the Hubble on basically a dark section of the sky, and then they just let the camera expose for, I don't know how long it was. And then when they looked at what they saw, it was just like, thousands of galaxies that just appeared out of nowhere, essentially. So imagine that, but on an order of magnitude more. That's my understanding of what the James Webb will be able to do. And also it sees in the infrared much more than the Hubble.
Yeah. Yeah.
I wonder, is it James that wants to come in or Paul wants to come in? But I wonder what our brother Hugh Ross has said, because the last quote he said that there's over, I think it's 50 billion trillion stars in the universe. If you go back measures of order, like Don is saying, right back to the backfield to the billions of light years, you're going to see probably billions times that. It's going to be so mind blowing. Would it not be?
Well, if you're going back in time, further back than what we've gone so far, you'll be able to see how maybe some of the first stars form, how some of the first galaxies form.
It's interesting that we can keep looking further and further away, and by looking further and further away, we're looking back in time, further back in time. But I understand you can never see the edge of the universe, no matter how far you look, which is kind of odd and interesting. And at the same time, there's no center of the universe. There's no edge to it as well.
And as
Well,
Bruno had in his
and I think
in your
because-
diagram, Bruno, you had something called the dark age, right? Where there's a
Pardon
wall that we won't be able to see back to the very beginning because of the nature of the early universe.
You can't see beyond a certain distance because you have a limiting factor of the speed of light, and because the universe is, because of dark matter, this expansion is increasing, so it's expanding faster and faster every year. So those distant points are moving farther and farther away from you.
Mhm.
So at a certain point, you won't be able to see them anymore.
Mhm.
There's a question in the chat by Peony, I believe, talking about saying that the majority of popular opinion is that there must be intelligent life on other planets because the universe is so huge, and it's just a matter of time before we find it. But these numbers here that I came up with, that reasons to believe came up with, where is it here? This number here of this such a huge low probability of life. This number is so small that we shouldn't even be here. That if you look at count all the total number of stars and planets that are in the universe, it's still not enough to even have life. The total number of particles in the whole entire universe a total number of protons in the whole universe is only 10 to the exponent 80. So this is like 10 to the exponent 970 times smaller. There isn't enough, atoms in the whole universe for this to be possible. This probability is so low. So it's when you're working with huge numbers, you think, oh, there are so many stars, a trillion, but that's nothing compared to this number. A trillion is only probably 10 to the exponent 30. Compare that to 10 to the exponent 1,000. It's such a huge difference. There's no way you can ever find a planet like this. But there's
Bruno, okay. Correct me if
Yeah.
I'm wrong on this, but if you're saying if we're limited by the speed of light, 10.8 to the meters, 10.8 meters per second squared. But if we move into the realms of like infrared and then measure like radiation, where we're gamma rays and alpha rays and beta waves, whatever it is, we're moving in instrumentation in that level, we're seeing the unseen. So is there possible then we're gathering in from a different electromagnetic spectrum, so we're pulling in beyond the speed of light, or what is that? How does that work exactly?
No, but you're only talking about all those different types of light you're mentioning are just different colors, basically. But they all still travel at the same speed.
Even the gamma rays, the alpha rays, and those electromagnetic waves. Yeah.
They
So
all
the
travel at the
constant-
same speed of light. They just have different amounts of energy in the light itself. Like a gamma ray has, a lot more energy than a ray of light of infrared. But they are both traveling at exactly the same speed.
Yeah.
So that doesn't matter. But the issue is this number of the probability of finding even one planet in the whole universe with life. This number is so small. You don't even have enough atoms in the whole universe for this. So this is way bigger or smaller than the total number of atoms, which tells you that the total number of planets in the whole universe is probably only like 10 to the 30 or 40, which is a very way big. How do I say? You just don't have enough planets in the whole universe for this to be possible.
A more graspable analogy is winning the lottery 150 times consecutively. That's the one I heard. I like that one. That is what it works out to.
Yeah, that's probably a better analogy.
Yeah, just not possible.
There's a question in the chat, Bruno, about other kinds of life that I think you addressed earlier. You might want to cover again.
Yes, people are thinking, some scientists are thinking, if there are carbon life is so difficult, what if you had life based on silicone? And silicone is an element that's similar to carbon. It has a valence of force, so it can also produce chains of molecules, like amino acids or proteins. But somebody, I think, tried that, and they couldn't get a protein that had more than 100 amino acids. So you wouldn't be able to have, insulin, for example, is a protein. I think it has 300 amino acids, and it's not even a complicated one. And there's other proteins that have way more amino acids in it, so you wouldn't be able to have a lot of proteins that are necessary for life. So carbon, I think is the only possibility.
Bruno, I'm assuming the word intelligent here is significant. I mean, I think perhaps they'll find microbes or bacteria on other planets, but as far as having intelligent life, that's the real kicker, right? That's the one that's.
Yes.
Yeah.
It's possible we may find life with bacteria
Mhm.
because it's not as difficult to make a planet where bacteria can survive. But then you still have the problem, which nobody has figured out. How does life start from non-living material?
Yes. Yeah.
Peony made a question here, another question here. about the Earth heating up. The core, as far as I know, is it changes the temperature of the core changes very slowly, but it actually becomes cooler as more and more of the uranium gets used up. I don't know why you have more volcanoes and earthquakes now, unless is there someone that knows why you would have more earthquakes and volcanoes at this point in history? I don't even know if that's really accurate to say that there are more. We have had, a lot of earthquakes, but compared to what's happened over the last, million years, I don't know how much more it is.
More expanded population, more record keeping, makes it look like more.
I have also heard that possibly the drilling into the Earth's surface, like through fracking, for example, extracting oil that's in between layers, that also weakens the crust, and maybe that would cause an increasing number of earthquakes because the crust has all the holes that people would drill through it. And if you do it in the right spot where there's already a fracture point, it can maybe cause earthquakes near there or further down the line of where the fracture goes.
Mhm.
So some of it could be caused by mankind.
Do you mind if I ask a question around, for instance, Nikola Tesla had developed some systems around free energy. The thing is the core of the Earth, how Bruno, like you said, it's like a solid nickel and iron core, and then there's this rotating centrifugal, but the reverse of that, the reverse of a centrifugal force, a centrifugal force going the other direction. So it creates this giant magneto, right? And it creates this magnetic force that comprises with the sun and the moon. Is there any way of triangulating, some of our astronomers and engineers conceptually triangulating the actual electromagnetic force between the sun, the moon, and the Earth, and kind of producing some type of like magneto and a motor system, like you have like Nikola Tesla style, to produce this free energy? Because one of the greatest problems in our world right now is how do you then produce more energy to run some of these huge systems that we have, even like our computation systems that are taking up huge stores of energy in our transportation systems and whatnot. And can anyone comment on that? Maybe we can put that together for another RTB, session or something around kind of some of these problems we have in our society with energy and the actual, different types of silicone substrates, for example, like the new 2 nanometer substrates we're trying to produce through new factories in Arizona and whatnot. Some of the great problems of our day. But anyway, that's more of a scientific exploration, perhaps engineering. But
I know that I have heard that Nikola Tesla did claim to have discovered this free energy, but I don't know if any of his work was actually published, so I don't really know much about it unless somebody else knows what he actually had discovered.
Well, I'm just wondering about, like, to your point, Robert, about all the different systems at play. But one of the other things that's generated is the so-called Van Allen belts, which protect us from cosmic radiation. So it's a very powerful system. Yeah, there's a great shot of it. Thanks, Bruno. And so the question is how to harness it. That's a different question. But these systems are incredibly powerful in terms of what they accomplish and what they do to protect us on planet Earth. Any planet with life would need it.
Yeah, you know that NASA and SpaceX are planning to go to Mars. One of the problems with getting to Mars is that you're not near the Earth. You're not protected by the radiation from the sun. So one solution that they thought of is to have a huge magnet on the ship that protects the astronauts inside from the solar radiation. I don't know, they're planning to go to Mars within the next, 5 to 10 years. So I don't know if that's what they're going to do or how they're going to stop all this radiation. But
I thought it was very interesting what you said about cause and effect, and when you were talking about Alzheimer's, and with it seemed like the answer to the problem was with diet, but also with external factors of the environment. And to me, that seemed to get into a simpler thing than what the medical community looks at as a cause and effect. So I wanted your opinion, because I broke that down a little further, and I came up with the understanding of something's cause gives us the variables for knowing that thing's effect, depending on our comprehension of that matter. Now,
I'm not sure I understand your question, but what Dale Bredesen discovered is that whereas most of this medical doctors are looking for a single drug that will stop
an
Alzheimer's,
effect, but they're treating an effect. They're not looking at the cause. And why are they not looking at the cause? And why are we as Christians not dealing with the cause? Because Solomon said it best about wisdom is the most. How's that go now? About understanding. Let me think here.
With all you're
No,
getting, get
wisdom is the
wisdom
most
and
important
get
thing to
understanding.
get, but with all you're getting, get understanding.
I'm not sure exactly what Solomon meant between the difference between understanding and wisdom, but what I was trying to say from all this is that you cannot a silver bullet and mentality. Like the silver bullet mentality looks for a single cause for a problem and thinks that if you just solve that one thing, you're going to find a solution. But in these three different cases I talked about, writing software, Alzheimer's, and just your basic health, there is no single one thing that you can do to get the good software or the your brain working and not having Alzheimer's and so on.
Well, I understand
things.
what you're saying there, because you're always going to have variables. But if you deal with all the variables around what you're dealing with, for example, the foundation of a building, if you make that building solid enough for that build, it's going to work. Now, if something, one of the variables isn't there, with the concrete not being strong enough, or the size of dimensions not being there, it's not going to work. But as long as you have all the variables there, that's going to function properly, because you're going to have the understanding of what that thing is and that you're trying to solve. Correct?
Yeah, but you're talking about having all the variables correct. So the same way you have all the factors that are needed for a particular thing that you're building has to be right. And if you don't get them right,
that requires the understanding of whatever you're trying to accomplish, because the understanding contains those variables for knowing. The understanding of the problem contains those variables for knowing how to solve it. So if I look at a problem, I'm going to look at it as the foundation of the problem. I'm going to build the solution up from there. Now, if I have all the components that I need from that foundational level, I'm going to be able to get to my solution stage.
Yeah. Well, yeah, but you have to have that understanding. Like you said, you're right that you need that understanding.
Well, that's why I said it was so important what Solomon said. Wisdom is the most important thing to get, but with all you're getting, get understanding. We're taught knowledge is power, but the truth is understanding is the on switch.
Yeah, I guess you could say that.
It's a beautiful presentation, though, Bruno. Thank you very much for all your work and contributing tonight. Everyone that's contributed, it's awesome.
You're welcome. So if no one else has any questions, we'll maybe end for tonight. And next month, like I said, we're going to have Fuzz Rana give a presentation on his book, which is called fit for a purpose. It talks about whether the anthropic principle applies to biochemistry. And looking forward to having him there. And I hope all of you can make it. Thank you for coming. If you have any other questions, like I said, you can send an email.
Just a quick question, Bruno, in regards to contacts. Like, if we have some questions around engineering or mathematics or astronomy, is there a list of the gentlemen and ladies that are on tonight that we may be able to ask them in questions that can help us kind of problem solve? We have some like ideas or solutions to develop some things. Is there some resources, some people that can assist, or how do we work in terms of contacts or reaching out to people? Any suggestions there?
We have available a much larger apologist network through RTB for those of us that are certified apologists. So we have access to a much broader audience than just the chapter. Certainly, if there are people within our chapter, we know who they are and we can reach out to them if you have questions. But the best is to send those questions to Bruno, and then he'll send them to the appropriate person. But there are many engineers and other types who are, certified apologists within RTB that can answer specific questions like that. So don't hesitate.
And remember, there is a number of books in my garage that I can always send you.
Thank you. Thank you, Jan. Do you want to do a quick ad? Why don't you do a quick advert, Jan? Tell everybody a bit more.
Yeah, there is. We didn't move too much over the last 2 years for obvious reasons, right? But it is still there. And I'm sending these books for the asking. The only thing is you have to pay for the book and for the shipping, which is probably in a range of $8 to $10, if I remember, depending on how heavy the shipping is. And also I can suggest that my dad's Word journal is now available in English. So if you're interested in this one, I'm willing to send you this one as well. It is available from Amazon as well. So yeah, that's the whole story.
Yeah, are you also willing to have people come to your home and pick up any book they order?
Oh yeah, absolutely. In fact, Robert is coming to me, I understand, tomorrow sometime, because he amazingly I was able to put together the full 2 sets for his apologist training, which he needs badly. I think he's going to save probably something like $60 at least on shipping charges from the US, which is, yeah, unfortunately it's very expensive.
That was going to be one of my questions, John, whether Robert was able to get a hold of you. So that's great that you guys connected, because I said that I figured you'd have everything in stock. So that's perfect.
Yeah. Thanks for
congrats to you, Robert, for taking the course. That's great. We congratulate you and we encourage you and all the best with that. That's awesome.
Yeah,
I'll be reaching out. I'll be stumbling and falling all over the place on the advanced astronomy design one for sure, as you can tell tonight.
But Robert, don't be afraid, because they give you lots of time. You can do things at your own pace. You don't have to stick to a specific schedule. They give you a time if it takes you longer.
What course is it you're taking, Robert?
Well, I'm starting off with, of course, the first one, so the Bible and creation, and then right now the ones that are running are the advanced astronomy and design. So I'm gonna go with that one, and those 2 to start off with. But my goal is to do the intermediate apologeticist certification, and then going to the advanced one, of course. And then I want to follow up with the university through Biola, and then eventually keep a long path. I want a pathway to go like for 3 years to wrap this up. But that's the goal. Yeah. Anyone else who wants to join me in it, let's do it together. We'll hop on the same train and go together on this one. 3-year train. It's really fun.
So it is the science and faith one that you're taking in January?
No, they've already started. So like the Bible and creation starts this week, and so does the advanced astronomy and design. But I'm actually auditing the advanced astronomy and design for now. But I'm doing the certification in the Bible and creation one to start because it's a bit advanced because like I mean take all that on at the same time because they're running concurrently, right?
Right.
Yeah.
Yeah.
But yeah, I'll audit, then I'll do the certification after. Probably do it again just for fun, knock it out of the park.
Yeah, they have an introductory one in the fall on cosmology.
Yeah, it was good decision, Robert, to do it one at a time.
Okay, thank you, everyone. We'll see you all next month, I hope.
Th-
And
Take care.
Thank you, Bruno. Great stuff.
Yeah. very
Thanks,
good.
Bruno.
you're welcome.
Bruno. Thanks,
Good night,
Bruno.
everyone. All the best.
Goodbye.
Night.
Thanks, Bruno. Bye-bye.
Right.